Okay, Bismillahirrahmanirrahim. Assalamu alaikum. Welcome back to the class of digital communication after the Eid break. And we will continue our discussion on analyzing the performance of your communication system in the presence of channel degradations. So we are looking at error performance of the digital communication system. And so we continue our discussion. In the previous weeks, the topics that we looked at are mentioned on the next slide. Okay, so these were the topics we studied in the later half of the previous week. So we looked at coherent and non-coherent detection to differentiate between them. Obviously, one of them requires to extract the incoming signals phase and so that it is able to generate a local oscillator of the same phase and frequency at the receiver. That is coherent detection. Whereas in non-coherent detection, there is no such requirement. This one is obviously better in terms of its noise performance, and non-coherent detection is obviously better in terms of its simplicity of hardware. So that's what we discussed last time. And then we also looked at the bit error performance of various modulation schemes by discussing the curve of the EB by N naught versus the bit error rate of different modulation schemes. So we looked at that curve and discussed that, and we also looked at the memory signaling and its error performance. Okay, so this week the topics that we're looking at include first of all the Shannon Hartley Capacity Theorem in the context of EB by naught, and then we will be deriving an expression for the Shannon limit on EB by naught, and thereafter we will be once again looking at memory signaling and their error performance. So a comparative figure, and then we'll move on to discussing a few features required in MATLAB and Simulink so that we are able to analyze a digital communication system on Simulink. And finally, so coming over to the learning outcomes for this part of the course. So in this lecture, the learning outcomes are that the student should be able to first of all conclude that there is a limiting value of EB by naught. So we cannot go lower than that without having errors on our communication system. Students should be able to realize that it is not practically possible to reach the Shannon limit, which we will derive. The student should be able to operate Simulink to analyze communication systems. And finally, students should be able to build and analyze digital communication systems in Simulink for its error performance. So these are the learning outcomes for this week. Now coming over to the first thing, which is the Shannon Hartley Capacity Theorem. We've already studied it, so we know what the Shannon Hartley Theorem is. That is expressed by this equation here. So this equation we are familiar with. That is the equation for Shannon Hartley Theorem, where C is the channel capacity and we assume a noisy channel. So this is the equation for a noisy channel. S here represents the average signal power. N here represents the average noise power, and W represents the bandwidth. So the channel capacity is dependent on the bandwidth available, the signal power, the noise power. It depends on these three things. And the bandwidth, as we know, is measured in hertz. The capacity is measured in bits per second. So what it is that it is theoretically possible to transmit information over such a channel at any information rate r, which is less than or equal to c, with an arbitrarily small error probability by using a sufficiently complicated coding scheme. So that is the full statement of Shannon Hartley capacity theorem. Yes, we can achieve this capacity. So our information rate can match this capacity with a small probability of error if we are using a channel coding scheme. in a noisy channel. So this is basically the crux of this theorem. If we try to exceed information rate beyond C, beyond this limit, so that is the limit. If we try to increase R beyond C, then we will not have a small probability of error. So our probability of error increases as we try to increase the information rate beyond C. As long as we are less than or equal to C, we are able to achieve our communication with a small probability of error, provided we are using channel coding scheme. But if we try to increase that, even if when we are using a channel coding scheme, we will not have a small probability of error. Okay, so continuing our discussion of Shannon Hartley capacity theorem. We can express noise power N as product of the noise power spectral density and the noise bandwidth. So if you want to know power, you multiply the power spectral density by the spectral bandwidth, so you get the power. So this is the expression for noise power. So in this Shannon Hartley capacity theorem's equation, we can replace N by its expression that we just mentioned above. So actually this expression then looks like this as given in the third bullet, as you can see here. So if I basically here I've divided it by W. So C by W is on the left hand side, whereas log 2 of everything else is on the right hand side. So that is how the equation for Shannon Hartley theorem is transformed at this stage. So C by W, we can say that is the normalized channel capacity, and if you look at its units, then its units are bits per second per hertz. So basically the hertz comes in the numerator, so its units are hertz per bits per second. You have to recall we derived that EB by N naught is a normalized version of signal to noise ratio, and in fact EB by N naught is equal to signal to noise ratio multiplied by W by R, where W is the bandwidth and R is the information rate. So here in this case, once again we can replace noise power N by the product of noise power spectral density N naught multiplied by its bandwidth W. So we can replace the N by N naught W in this expression of EB by N naught, and then the W's, they cancel each other. So we are left with this expression for EB by N naught, which is equal to S divided by N naught multiplied by R. Now if R, the transmission rate, is equal to the channel capacity C, then we can make another substitution. So EB by N naught in that case will be equal to S divided by N naught multiplied by C, where C is the channel capacity of the Shannon Hartley capacity theorem. Now from our Shannon Hartley capacity theorem, we can say that the S by N naught W, that is basically equal to S by N naught into C multiplied by C by W. So if you multiply and divide it by C, that is what you get. And we know what C by W is. Yes, so C by W is equal to this, and basically substituting from the above equation, then C by W, the expression for C by W, it becomes this. And if we take anti-log, then we get this. So 2 raised to power C by W is equal to 1 plus EB by N naught multiplied by C by W. And if we rearrange for EB by N naught, so this is the expression for EB by N naught. So we started from Shannon Hartley capacity theorem. We used our already derived expression for EB by N naught, and we made substitutions in both the equations to arrive here at this expression for EB by N naught. So we come to the point where we have to realize that there exists a limiting value of EB by naught below which there can be no error-free communication at any information rate. So there is a minimum value of EB by naught below which no error-free communication is possible no matter how low the information rate is. And if you want to find that value, we have to use this limiting expression, this series expansion. So limit x tends to 0, 1 plus x whole raised to power 1 over x is equal to e. So if we use this, we can calculate the limiting value of EB by naught as follows. So let's say that x is equal to EB by naught multiplied by C by W. If we assume that that is x, then the expression that we derived on the previous slide, okay, that will look something like this. And C by W is basically equal to that. You can verify. Okay, so then in that case, it simplifies to this. And in the limiting sense, as C by W approaches 0, this is what we get, if the value for EB by naught, if applying that limit, the limiting case. So we are left with almost a value of 0.7. That is the numerical value of EB by naught. And talking in decibels, EB by naught is equal to minus 1.6 dB. So this is what we derive by applying this expansion, series expansion, to our derived expression of EB by naught. And this value of EB by naught, this is called the Shannon limit. So this is that limit, this is the limiting value of EB by naught, and below this value there can be no error-free communication for any sort of information rate. Now using this, where has it been used? You have seen it, but you didn't question it, so we will look at a curve again. So if you look at this curve here for memory signaling and its error performance, so we have the bit error probability PB on y-axis, and we have the EB by naught expressed in decibels on x-axis, and you can see the curves for different values of k. Now k here, it represents um, the number of bits behind each symbol. So as k increases, basically the modulation scheme is increasing. You know, when k is 1, we have the binary modulation schemes. When k is 2, that means every channel symbols or every modulation symbol is represented by 2 bits. So then we have 4 level modulation. When k is 3, we have 8 level modulation. When k is 4, we have 16 level modulation, and so on. So the modulation scheme is advancing as k is increasing. So this curve here is showing you a comparison of different modulation schemes. Okay, we have seen this curve previously, so we are looking at it again. So these are different modulation schemes of a particular type of modulation, only the level or the complexity is changing. The modulation scheme is the same. Okay, so number of channel symbols or the number of modulation symbols or the number of modulation levels, that is increasing. So here, if you look at the Shannon limit is the PB versus EB by naught curve corresponding to k is equal to infinity. This curve here. If you look at this curve, that is the ideal curve, and where it intersects the EB by naught axis here, that is the Shannon limit. This is the Shannon limit of minus 1.6 dBs. And when will we reach this? When we have k is equal to infinity. And this curve itself is discontinuous, as you can see, because it goes from the value of PB is equal to 1 by 2 here. This is 1 by 2. So let me mention that. So the value here is 1 by 2. Okay, so this curve goes from 1 by 2 to PB is equal to 0. So it goes to 0 at EB by naught is equal to minus 1.6 dB. So suddenly its behavior changes from 0.5 to 0 when we have EB by naught as minus 1.6. And that is obviously, as you can understand, that is something which is not practically possible. So in reality, it is not possible to reach the Shannon limit. We can keep on increasing k, but we can never have this straight line because of practical limitations. Because as k increases, the bandwidth requirement increases. We know the bandwidth requirement of 256 QAM is more than that of 16 QAM, which is more than that of 4 QAM. So as K increases, the bandwidth requirement increases, and also obviously the hardware complications increase. We need to have a very complex hardware, a very sensitive receiver. So for all these factors, we can't really approach this limit. So we will always be somewhere here. So that's what we need to remember, that there is a limit on EB by N naught, which we cannot even attain practically. And even if theoretically we were able to attain it, beyond that, we don't have error-free communication for any information rate whatsoever. Okay, so now we want to extend our analysis of error performance to MATLAB and Simulink. So you need to have MATLAB and Simulink installed on your laptops or PCs. So if you haven't done so, you need to do it. Okay, I had told you that we will be needing it. So you might have as well have done it. You will also need them for lab related tasks. So you must have MATLAB or Simulink installed. That's the first thing you need. And secondly, you have to check your versions, because the instructions sometimes or the commands are different based on different versions. So there is a way of checking your version. So when you start MATLAB, okay, so when you click on the MATLAB icon and it takes some time to load, once it's loaded and you see the main MATLAB window, command window, so on that home screen, if you type VER without the commas, if you type VER and press enter, then the MATLAB will be able to show you whatever is installed. So it lets you know which MATLAB version is installed, your MATLAB license number, as well as the Simulink version that is installed on your system. So that's not the only thing that it tells you. It also tells you which toolboxes or block sets have been installed. You just need to remember that in order for you to progress further for digital communications course, you must have Simulink and communication system toolbox installed in addition to the main MATLAB software. So this is the minimum requirement. That is what you need for this course. So make sure you type this and you press enter and you know that you have these things installed in your laptop or PC. So just a quick note that the communications block set was introduced with MATLAB release 12. So the communications block set basically incorporates the functionality of the blocks that were included in the communications toolbox in the previous releases. So if you have the new release, you will not have the communication toolbox now. You will have the communication block set, but that includes all the functions of the previous communication toolbox, just in case somebody is using release 11 or any previous version. So continuing on our discussion on MATLAB and Simulink, once you load MATLAB, you've checked your versions, you've got everything. So you've got the all the three things that are needed for this course. So you type com startup in the MATLAB main window and press enter. That is needed before you simulate any communication system that is required. So remember, make it a habit. Every time you start up MATLAB and you're about to do a simulation or create a communication system model, that is the first thing you need to do. What it does is that it sets certain Simulink preferences to values that are most appropriate for the simulation of communication systems. Okay, so you will also see this message on the MATLAB main interface. After you have done this, you will see this message: change default Simulink settings for communication system models. So this when this message appears, it's a confirmation that the command has been accepted by MATLAB. So what we are going to do firstly in MATLAB or Simulink is that we are going to look at the effects of noise on a digital communication system. So we will discuss an example to go through how we can analyze a digital communication system on Simulink. And for that, we will start off with a built-in example in MATLAB Simulink, and that built-in example can be activated if you type com phase noise in the MATLAB main window and press enter. Okay, and just a quick note, if this command gives an error, you probably have a different version of MATLAB or maybe a newer version of MATLAB. So if that gives an error, then type the same command but with a doc underscore. So it's doc underscore com phase noise. Type this and then press enter. So either this or either this, any one of them will open the built-in model that has already been created in MATLAB, and that is what we are going to use to analyze the effects of noise on a digital communication system. So when you do that, what will you see? It will take some time, but it will load a pre-designed, pre-saved model. And that is basically the title of that model is phase noise effects in 256 QAM. And that model will look like this. So this is what you should be looking at after you are following those commands that I mentioned in the previous slide. So as you can see, this is the digital communication system on your screen. The first block, so we will have a quick discussion of each block. So the first block here is a random integer generator. So that generates random integers which represents your data. And then we are skipping other blocks. So we directly go to rectangular 256 QAM, which is modulation. So you can also see from the symbol here. So it is getting digital data from the previous block, and it is using this digital data to modulate an analog carrier. Okay, so that is what QAM does. So it is modulating the amplitude and phase of this analog carrier. And now the modulated carrier, one of the symbols in every symbol interval, will pass through the channel. So we have assumed or we have taken AWGN channel as it says here. So AWGN channel. And then we've also added phase noise. So the channel itself is noisy, which is introducing noise in the amplitude, and we've also added this block which adds phase noise to the system. So this is amplitude noise, this is phase noise. So after passing through the channel, getting affected by noise, we receive our signal. So basically this after phase noise block is our receiver, and we are looking at our noisy received signal using this, the constellation diagram or the scatter plot. Okay, so we are looking at that here, and then it gets demodulated once again by the block which says rectangular 256 QAM. That's the demodulator block. And then once we have demodulated it, then we have the error rate calculation block, which is basically trying to determine if there are any errors. So basically it is comparing what it receives, the bit combination, the digital data that it receives, to the digital data that was originally transmitted. So it is comparing them to calculate the error. So error rate calculation takes place here, and then the last block is display, which displays the errors. So in the display there are three values. The first is symbol error rate, SER. The second is the total number of errors observed till that time, and the third is the total number of symbols transmitted at that time. So that is basically what this digital communication system has. So it is analyzing the effects of noise on 256 QAM, and then the blue shaded block here which says display figure. If you double click on this block, so you are able to see a bit error rate plot showing the performance of 256 QAM with various levels of phase noise. So that is what we will be doing next in our interactive session on MATLAB.